Welcome to Chapter 4. We're going to solve a two-dimensional heat transfer problem in a slab, and this is the quintessential problem for every transport phenomenon class. This chapter is going to be an example of problem-based learning. The entire chapter is one problem, and it's going to take us the entire chapter to solve it, but in so doing, we're going to develop the mathematical techniques that we'll be using throughout the module. So, let's jump right in and have a look at the problem we're going to solve. Heat is transferring through a two-dimensional slab. To ensure that heat transfer is in two dimensions, we're going to isolate the top and the bottom using insulation. And that's what that kind of gray fuzz is. 3 of the sides of the slab are held isothermally at temperature T1, and the 4th side is isothermal at T2. And I realize it's a little bit difficult to see in such a stationary plot. All right, let's take a look at our slab in sort of a three-dimensional depiction. So we have a coordinate system that's right-handed. It doesn't matter if it's right-handed or left-handed. The one in your notes is left-handed. And this is showing us that on the top and bottom of the slab, this gray stuff is our insulation. And that corresponds to positions of y equal to 0 and y equal to y max, whatever that value is. Now, 3 of the sides on this slab are held isothermally at a cool temperature, indicated by blue here, and that's temperature T1. The 4th side is a hot isothermal side at temperature T2, right? So our job then is to take this physical depiction of the slab and translate it into mathematical boundary conditions. So the way I would go about doing this is looking at one plane at a time. We'll start with this plane, and we notice that it's a YZ plane. And so the coordinate that's going to define this plane is the x-coordinate, because that's the coordinate orthogonal to the plane, and so it tells you where that plane is located in space. So this plane, this boundary condition, T1, is going to be defined by x equals some value. What value is it? Well, you just have to look at the position of where you've set your 0. Our 0 is set here. So this plane is x equals 0. And so your boundary condition then is at x equals 0, t equals t1 for all values of y and z. We don't specify y because y is not varying at all temperature is not varying with y at all in this problem, so we don't need to mention y. Now, if we're looking at this plane, this is an xy plane, and so the way we specify that is using a z-coordinate. Again, we ask ourselves, which z-coordinate? Well, if this is 0, that means this is the z equals 0 plane. All right, if we come over here, this plane is a yz plane, so you specify it with x, and in this situation, x equals L. And finally, this is our hot plane, T2. It's a yx plane, so we specify it with the z-coordinate, and this position is z equal to L. So t equals T2 at z equals L for all values of x and y. Hopefully that makes sense. Now, the one thing we don't see here are any actual gradients looking like a temperature profile. And that's because the gradients are going to be entirely in the xz plane, this plane, but we don't see them here because we haven't yet peeled off this insulation. So this is the plane where we're going to actually get the solution to our heat transfer problem. Now that we've had a good look at the geometry of the problem, let's write out the equations related, starting with the governing equation. We're going to use the heat equation, obviously. So last week we learned that the Laplacian of temperature plus the generation term equals 0 for steady state, and in this case we have no generation. our equation collapses to the idea that the Laplacian equals 0. This is relatively easy to solve. If we expand that into Cartesian coordinates, we have 2 second-order derivatives, which means that we need 4 boundary conditions for a particular solution to this problem. We have 4 temperatures specified spatially in this problem. Those are Dirac-Clay boundary conditions. So 4 boundary conditions, we'll be able to solve the problem. Next, we need to write out what those boundary conditions are. So we'll start with the YZ plane, and those are on the 2 sides of this box. Both of those planes are at temperature T1, and because it's the YZ plane, we know the coordinate we're going to use to specify it is the x coordinate. So we'll say at x equals 0, T is T1, and at x equals L, T is T1. So that's how we would write it in common notation. The more correct way of writing this is that the temperature at coordinate x equal to 0 for any value of z equals T1. And the same for position x equals L, any value of z. Okay, so now the next 2 planes that we have to specify are the xy planes. And the one that's closest to us is at temperature T1, but the one at the far edge of the slab is at temperature T2. So it's an xy plane. We're going to use the z coordinate to specify where it is. When z equals 0, that's the plane closest to us, the temperature is T1. And when z equals L, that's the further plane from us, temperature equals T2. And that is true for all values of x. So now we have 4 boundary conditions, and we are ready to start solving this problem.